Yes, Bhavna, if you can respond that the screen is visible and I am audible.
Yes, sir.
Okay. So we will start. Basically, it's time. So in the last lecture, basically it was some times ago, maybe on 2029th of October. So I just basically I will revise a few things in maybe a few seconds or few minutes so that we move ahead with the lot of content which we need to cover. So we were doing basically stationary processes last time, and then we discussed ergodicity, and we then came up with the concept of power spectral density. So this is all very important for us because of the noise effects, we need to model our transmission and reception over you can say a random system. It means, let us say, even if you don't consider wireless communication, then whatever you are receiving will be corrupted by some random signal, okay? And that random signal we refer to as noise, okay? So because it is being corrupted by a random signal, so the signal which we received ultimately or which we receive at the receiver is also a random signal. So we need to know the framework in which we study random signals. Okay, random signals. Now, what is the meaning of saying random signals? It simply means there is some variation with respect to time, and that variation is random. Okay. Up to now, we have studied random variables, but now we are studying random processes, which says that it is a category of random signals. Okay, we did one or two examples, and then I think we discussed this autocorrelation function, and then we came up with the concept of PST. Now, why this PST is required? Because this will be used to define the SNR, that is EB by N naught. Okay, this N naught is nothing but the power spectral density of the noise. That I think you have come across EB by N naught several times, maybe in one of the two courses earlier, or maybe in the current course itself. So we were at this point. So let us start. Okay. So before starting, let me just revise some. Basically, I let us revise the introduction to random process. Okay. So we were studying random processes. What do we mean by them? Okay. So random processes. Okay. Variation with respect to time. Let us say in our context. Okay. Although random processes can have variation with respect to location also and several other parameters also, but for our purpose, we study variation with respect to time, and at each time instant, the value taken is random. Okay, so that is simply in easy terms. Okay, for our purpose, let me write it now. For our purpose, because this should not be confused that random processes will have variation only with respect to time. They can vary with respect to location also. They can vary with respect to several other parameters also. Basically, let us say if you call it to be a parameter, okay, it means if the parameter changes a value, the value which the signal will take is random. Okay, so that is what we are saying, that if we say that x of t is a random process, then for each t, x of t is random. Okay. Sorry. Now we came up with another way to characterize it, is omega and t. Now what was this? See, this x of t is somewhat confusing because we have been habitual of studying x of t in the form of deterministic signals, that is a cos omega t, or any sort of time variation which we know, for example exponential functions. So how do you differentiate with such a representation with the standard representation of deterministic signals? So I think the authors, or it has been a trend that we take x of omega, you can take a comma t, or you can take this colon t, whatever, okay, and comma with a dot. So what do you mean by this? Now suppose you run this experiment. Now you run the experiment several times in the same setting. For example, you do it. Suppose I define the number of phone calls that come from 9 a.m. to 10 a.m. at a call center. Okay. So let us say number of calls. Now you do it every day. Now record this, do this measurement. Do this measurement for a year daily. Okay. So what it is? Suppose if I say that this is 9 a.m. to 10 a.m. and this is this number of calls. Okay. Or you can say that, let me be more specific, instead of, let us give it a chart, because you will have a call center with multiple telephones. So suppose you divide 9 a.m. to 10 a.m. into 5 minutes of time interval. That is 9 to 9:05, 9:06 to 9:11, 9:12 to 9:17, and this goes on. Okay, and this is, let us say, 1st of January 2021. So suppose this is 5 calls received, then this is our 10 calls received, and our 11 calls received, and this. Now this experiment goes up to 31st of December 2021. Okay, so this, let us say this gives 6, 7, 2. So this is a sort of, if I call that this is a discrete sequence. So how many sequences you will get? Maybe 365 sequences. Okay, you will get 5, 10, 11, 15, 6, 7, 2, and such. This sequences will continue. Okay, so you will get 365 sequences. Now this omega generally represents this, that the different trials, okay, and this t varies like this. So this is t and this is omega. So after performing the experiments, if you collect all the possible waveforms, okay, that is, after running experiments several times, you collect all possible xt's, then you can represent it by x of omega comma t. Okay, but this says that omega represents the number of trials, different trials of the experiment. जैसे कि let us say that you need to transmit one file, you transmit a text file daily at 9 a.m. to a receiver. Okay, same text file. So you will observe that, let us say, over 30 days, if at 9 a.m., suppose it takes 2 minutes to transmit this file, so at 9:02 a.m., if I check at the receiver the signal which I receive, we will observe that daily you receive a different waveform. Daily. So there is a different waveform each day, that is what you receive. So this is characterized, or this is, you can say, enumerated, although it is not possible because you may not have a countable thing. This is different trials. So this is one trial, this is one trial, this is one trial. So this is represented by omega. And this variation, which is happening through time, is represented by time t. Okay. Now you fix t. Suppose you say that I am observing it at t equal to 9:01 a.m. Now if I ask that at what value the process will take at 9:01 a.m., so you will say that it is a random variable, because if you check the omega space, that is all possible waveforms you check, so you cannot say what value it can take. Okay, it can take any possible value. So at each time it is a random variable, and hence, because you do not know that what value it will take at the next time instance. Suppose if I take t prime is equal to 9:011 a.m. Okay, you are given that what value it will take at t equal to 9:01 a.m. But you cannot say what value it will take at t prime equal to 9:011 a.m. because the sample space is so big, you do not know which waveform you are observing. So ऐसा नहीं है कि आपको बता दिया जाए कि ओमेगा, अगर ओमेगा 1 है, so then you can tell that what value it will take, because this sample space is quite big. Okay. Once the experiment is done, let us say now you are sitting at 9:05, 9:02. So you have observed the waveform from 9 to 9:02 a.m. You have observed it. Then so you can tell that if you are given a value at 9:01, what value it will take at 9:01. That you can tell because you have observed it. So unless you have observed it, you cannot say what value this process will take at the next following time instant. Okay. So this is, you can say, a very small introduction to what random processes is, and you should not confuse between these two notations, because at a lot of places the authors will start with this notation x of omega comma t, but they will subsequently shift to x of t. Why? Because carrying such a notation wastes the space, and they assume that it is clear from the context, and it should also be clear to you as well. Okay. So now let us come back to what we were doing. Okay. Let's see. So I think we were here. You were deriving the power spectral density. Let us check. Okay. So we said that let x of t comma ei represent. So this ei is nothing but one of the trials. Okay. So now if ei is given, this t is now this is the function of time. Okay. So this is represents the sample function. That is what is. This is a sample function. Means one of the possible values which x of t will take for whole t. That is the meaning of sample function. Okay. So you are saying that represent sample function of random process xt. Let us define a truncated version. We defined a truncated version, and we took its Fourier transform. And then we said that let us say what will be the E of t, that is the energy of this truncated signal. Okay, and we use the Parseval's relation. What ultimately we are doing is we are basically connecting power to power spectral density. Okay, now what is the meaning of power spectral density? Let me just write. So we start from where we left in lecture number 20. Okay. So PSD is nothing but power per unit frequency. That is the meaning of power spectral density. Okay. Density will simply say that एक point पे कितना है. Spectral means the frequency and power P represents the power. So that should be clear from the name itself. Power spectral density, it means spectrum के respect में power कैसे distributed है. So इसको हम derive कर रहे हैं. So I think what we did was last equation is okay. So we said that et is a random variable. So what do? Is we take our average. Now what is happening is that we have taken a sample function. Now the sample function, if we want to say something about the random process as a whole, doesn't hold that much value, because this is one of the possible realizations of the random process. So you have to take the expectation, or you have to take the ensemble average, so that you come up with something which you can comment about the random process as a whole. So we took the expectation. Okay. So now we will start from this one. I think I wrote that we have to take the ensemble average. So I will start from taking the ensemble average. You can say ensemble. There are several possible ways. So let me represent this ensemble average by E of t bar. Okay. This is equal to minus t by 2 to t by 2. Now you take the ensemble average of x square t dt. Okay. Or let me just represent this also by the expectation, so that it is clear. Okay. Now this is what? This is a function of time, because this is evaluated for a particular time t. Okay, that is evaluated at a particular time t. Okay. Now this is equal to integral, if you just use the Parseval's relation. So this is nothing but xt. Sorry, right now we are not using the Parseval's relation. We are just representing it by the truncated form. dt. Okay. Which is equal to, now if you use the Parseval's relation. Now this expectation will go inside and you will have this. The Fourier transform of the truncated version. Okay. You know that why this xt of f is also a random variable, or sorry, random process, because you are taking the Fourier transform of a sample function. Okay. Let me write that xt square f or xtf is also a random process in frequency because it is the Fourier transform of a sample function. You must know. So sample functions itself are, you can say, random. You do not know which sample function you really observe. So if it is of a particular sample function, then this will also be a random process, you can say. Okay. Means this XTF will change as your sample function will change. So you will observe for a particular XTT, you will observe different XTFs. So the expectation then easily moves to this random process as well. Okay. Now with this as the base, let us now start. This is the mean. This is called as the mean normalized. Let me write. This is called as the mean. See, I am following this from Couch's book because I found that definition and everything there very, you can say, proper. I mean normalized energy. Now, what is the meaning of this? So, Couch refers to this as normalized energy because he assumes that your value of resistance is 1 ohm. So, I would say that read chapter 2 from Couch for building the base. Read chapter 2 from Couch. Okay. So this will clarify a lot of concepts in your mind about how do we define energy and power in circuits. We assume that the value of R is 1 ohm. To highlight this, we say that it is a normalized energy. Now, once we take the expectation, this mean comes. Okay, so this is mean normalized energy. If you don't take the expectation, he uses the notation as normalized energy. And in several textbooks, you might find the notation as only energy instead of normalized energy. So let us now define the normalized average power. Okay. Is the energy spent per unit time. Okay. Now this normalized again here refers to the value of resistance being 1 ohm. Okay. And this average power now here, although power is generally defined as an average with respect to time, but here we have taken the expectation also in addition to it being averaged over time. Okay, let us see. So P, the standard definition is limit t tends to infinity. See, you have to go and read chapter 2 from Couch, or you can go and read any book on signals and systems to revise this definition of power in this manner in which I will be doing. Okay, as well as energy. This is simple. I think you can recall that this is the way we used to work in signals and systems. That is the way we define power. Okay, so we used to do like this. Okay. Now the point is we will take an expectation also. So here will be the expectation, because otherwise this x square t or this power itself becomes a random variable. Okay, we don't want it to be a random variable. Now why I am calling p to be a random variable, because time will be averaged out, so p becomes a number. So for each sample function you get one number, and because sample functions themselves are random, so this p becomes a random variable, not a process. Here xtf becomes a random process with respect to frequency. Okay, because frequency is a variable which varies, and for a particular frequency f, you do not know that what the value would be, because you do not know at a particular time what value the process will take. Okay, so this xtf is a random process. This p becomes a random variable if you don't take this expectation. Now when I have taken an expectation, so this becomes an average with respect to, now this is an ensemble average also and time average also. So this gives you a number which is, you can say, would represent a property of the process, okay, as a whole. So this is given as limit t tends to infinity 1 upon t. You can write in this manner. Okay, this expectation is carried. This is equal to integral. Now we exchange this expectation, we exchange this integral with the limit. Okay, limit t tends to infinity, 1 upon t square df. Okay, so this is, you can say, okay. So this is, let us take, if you take this limit and 1 by t inside, okay, and let me write this expectation as well. Okay, let me take the mu. Because putting everything is difficult. So this is a very good, you can say, derivation of PST. Otherwise, what happens is that we are told that, let us say, there is a PST and everything, but we don't know how really it comes. So as engineers, we must know this. Okay, this is limit infinity 1 upon t expectation of. Okay, so this says that you just obtain this quantity and then you integrate. So let me be very specific now. What is this? Let us see from this. This is, you can say, A. So this shows that for a random process, the average normalized power is given by the time average of the second moment. What is it? Let us see from A. What is this expectation of x squared t? This is the second moment. Okay. For a particular time, you will evaluate this second moment, and if you take the time average of the second moment, then you get the power, average normalized power. Okay. That's why I've written it A. I think like bracket I should write CA. Okay. Now, if xt is wide sense stationary, okay, you need to go back and revise this concept from, I think, lecture 20 and 19, that what do you mean by stationarity and then wide sense stationarity. Then time average any sample function is equal to ensemble average of x squared t for any t. Okay, because this is constant, because this is constant. Why? Because we have seen that for wide sense stationary processes, if I try to find out expected value of x squared t for a particular t, it is independent of t. It is independent of t. Okay. So this is what you can go back and revise. So now let us define the PST. We will define the PST from this. This is PST. Okay. This is really your PST. Why? Because if I am integrating it by multiplying it by df and then I am integrating it, I get the total power. So this gives me the power distribution with respect to frequency. So from, you can say, you can observe B. From observing B, we can define the PST. We can define the PST. PST for a random process x of t as, so this is P of xf is nothing but limit t tending to infinity, expected value of whole square divided by t. Okay, that is what we have done here. And the units are watt per hertz. This watt, W should be big. Why? Because the unit of this is joule per hertz. Okay. Now this T as seconds, so joule per seconds per hertz. So this becomes joule per second per hertz. And joule per second is nothing but watt. Okay. But it becomes watt per hertz. So per hertz means that this becomes a power spectral density. That will tell you that what is the per unit of frequency, what is the power consumption. So if you integrate it by multiplying it by df and you just add all of them, that is, you find the area under pxf, this will give you the total power. Okay. So where your xtf is equal to, that is, this I am repeating, minus t by 2 to t by 2. That is nothing but the Fourier transform minus j2 pi f of t dt. Okay. And the total power can be easily obtained by integrating or by finding the power area under the PXF graph or a PXF function. Okay. So this is what is the power spectral density is. So why we have shown it this way is because we must know that from where does it watt per hertz comes and what is the way to obtain it. But this expression is quite complex. What it says is that you need to obtain the expectation of this for a particular f. Let us say f is equal to f1. So for this f1, you need to obtain this ensemble average. Then you have to divide it by t sum, and then you have to tend t to infinity. Now, even if you fix f as f1, then t is changing. So this is quite a cumbersome, or you can say a difficult expression to obtain if at all we need to work fastly, or if we need to have a representation which we can play with. So there comes the Wiener's theorem, which helps us. This we must know that from this we have basically studied all of our communication system. This theorem helps us a lot. We just state it. There is no need to prove it. We just need to use it. So when x of t is a Whitesian stationary process, is a WSS process, the PST, instead of obtaining it from this expression, you can obtain it from the Fourier transform of the autocorrelation function. The PST can be obtained from Fourier transform of the autocorrelation function. Okay, that is P of xf can be obtained as the Fourier transform of, because this is a Whitesian stationary process, your autocorrelation depends only on the time shift. It doesn't depend on the value of t. I think this we have covered. I think most probably we must have covered. Let me just check. Yes, I think autocorrelation we defined. Yeah, and then we said that It is if it is stationary to the second order, then it depends only on tau. Okay. So this is given by integral minus infinity to infinity Rx of tau e raised to power minus j 2 pi f tau d tau. Okay. So I am not stating a few conditions in which this theorem is valid, or let me just state them. We do not need them for our case because we do not work generally with signals which are not well defined or which have some issues. At least not at the undergraduate level. We are happy to work with, or we are satisfied, or we only encounter happy functions. It means those who satisfy the properties stated by the theorems. Fourier inverse of Pxf. Okay, and this is simply, I am just stating the formula. This you already know. Inverse Fourier transform. Okay, so with some conditions. That's why I'm saying that these conditions we need not know right now, or we need not check. But the functions which we encounter, because generally they satisfy this on Rx tau, such that is with some conditions. Okay. We want that this integral tau and the absolute value of Rx tau d tau should be less than infinity. Okay, I think this comes from few properties of the Fourier transform as well as several other things. But right now, for our case, we need not check that if the autocorrelation function of the signal we are encountering satisfies this or not, because mostly they will. Or right now, the focus of the course is not on this theorem, but on the application of this theorem. So, if we need to apply, then the signal must satisfy the conditions proposed by this theorem. Okay, so that is what this power spectral density can be obtained by the Fourier transform of the autocorrelation function. So, you do not need to evaluate this expression. That is what this theorem will help you. One important thing that we have stated this theorem for WSS processes, but what happens if the process is not WSS? So we will do that for the sake of completion. Let me note it down. Note that this theorem is also valid for a non-stationary process. Okay, this is valid provided that we replace Rx tau by the time average of Rx. Okay, so you have to obtain the autocorrelation function and we replace it by the time average. Then this theorem will also apply to non-stationary processes. But right now, in our case, most of the processes would be stationary. That is a noise process or whatever we would be taking, or the information or the process which models the information also would be cyclostationary. So you generally won't need to use this Rx t comma t plus tau. But we must know it. That's why I have written it. So now we will do one or two properties of PST. Okay. So what are the properties of PST? The first property is, you can see from this that because this is absolute value whole square, then this is an expectation of such a number. This will cannot turn out to be positive. Okay. So first of all, Pxf is always real. Let me now write P more properly, whatever I have been using. Pxf is always real. Okay. Second, Pxf is greater than or equal to 0. I am stating few properties. I think they are clear from the way we have derived it, so I am not elaborating that much. Integral minus infinity to infinity, Pxf, Tf will be equal to P, which is equal to total normalized power. Now this normalized simply means that value of resistance R is 1, normalized power, when x of t is White's and stationary, integral is equal to P, which is equal to the expectation of x square, okay, which is equal to Rx0. Now I have not written T here because we have assumed the process is White's and stationary and this would be independent of time. That's why I have not written T here, okay. And this is nothing but the value which the autocorrelation function takes at 0, okay. That is a shift tau as 0. The fourth property, they are very easily verifiable. That's why I am not basically doing the verification. This is left as a homework. Verification of all properties is a homework. Okay. So Pxf, Px0 is nothing but Rx tau d tau that we know. And fifth one, this will be when xt is real, Px of minus f will be equal to Px of f. Okay, I think this you can recall that when the xt used to be real, the Fourier transform, that x of f is you can say the magnitude spectrum is even and the phase spectrum is odd. From there you can easily relate. Okay, ultimately proving it will require some steps, but you can relate from that fact. Okay. Now we come to if there anything to say, you can definitely, you're most welcome. But otherwise, we will be moving ahead. So now we come to the important concept, that is white noise process. Now, what is this? So with the background which we have built, and how it enables us to study this. Okay, we will abbreviate it as WNP. That is white noise processes. So which process? I have not used Gaussian here. Remember that Gaussian is not here. Right now we are only studying what is a white noise process. If that process has a density that is Gaussian, then we call it as a white Gaussian noise. Okay, remember this. So first of all, let us characterize what is a WNP. So a random process x of t is said to be a white noise process if the PST is constant. That is important. That's why the word white comes. That white means that it doesn't differentiate in the frequency. That is what you can say. It is uniform. It takes the same value across all the frequencies. Okay. If the PST is constant, the PST takes a constant value. Okay, not the function, not the process itself, over all frequencies. Okay, that is Pxf is equal to n0 by 2. Suppose if we say n0 is a positive constant, because it's associated with PST. PST is always positive, and which implies that your Rx tau is nothing but a delta function. Okay. Why? Because you must know that what is the Fourier transform of delta function? That is 1. So if I take the Fourier transform Rx tau, I will land up with n0 by 2. Okay. Now when I land up with n0 by 2, it means This is not n naught by 2 into delta of f. This is n naught by 2. It means if I just now vary f, I will get n naught by 2 at all f. So this is what is a white noise process. Okay. You can check by taking inverse Fourier transform. You can check by taking inverse Fourier transform of Px. Okay. Or you can take the Fourier transform of Rx tau and then you can check. But the definition, standard definition starts with Pxf. That's why I would say that take the inverse Fourier transform of Pxf and then find Rx tau. Or in other words, you can say that if the autocorrelation function is a delta function, okay, it means the process is, if at all delta is not 0, so the autocorrelation becomes 0. Suppose delta is equal to 1. So if delta is 1, sorry, if tau is 1, then delta of 1 is 0. So this Rx1 is 0. Okay. So for any shift, the process is uncorrelated. Now, example. Let us take an example. So thermal noise, which is generally in the circuit. So thermal noise. With this background, if you go back and study Haken's book, so in that book, in chapter 2, the author gives you short noise and thermal noise. So now you will understand what he means. Means if you read the description there, thermal noise can be considered to be a white noise process, over the operating band, where, so therefore this is generally taken, this is the Boltzmann constant, and I think T must be some temperature. It has a Gaussian distribution. It has a Gaussian distribution. Of note, this is important. I think I would say really important from the perspective of concept. It is possible to have white noise with other distributions. This is important. Okay, this should be basically remembered. That's why अगर ऐसा होता कि if that is the case that white noise is always Gaussian, then there was no need to put a G in between. That is, we say WGN when we say white Gaussian noise. So it means we need to say that the distribution of it is Gaussian. अगर ऐसा होता कि white noise की सिर्फ और सिर्फ Gaussian ही density होती, there was no need to put G. White noise then implies that it is a Gaussian distribution, but that is not the case. Okay, white noise simply says that the PST should be n naught by 2 or should be a constant across the frequency. Okay, so if at all that is the case, then it can take other distributions as well. But in our case, because thermal noise is one of the biggest sources of corruption and it has a Gaussian distribution, we call it as WGN. Okay, so this is what all base we wanted from, you can say, random processes. Now we need to study the Gaussian random variable in Gaussian process, not in deep, but at a level where it helps us study the receiver design. Okay, so I will just do a small revision. Okay, so the topic of study now is revision. I know that you have gone through Gaussian random variables and even multiple Gaussian random variables in your course on probability and information theory, but let us revise it somewhat. So revision of Gaussian random variables and you can say introduction. Okay, so this is important. This is now ultimately हम लोगों को आना इसी पे था, Gaussian random process पे. But क्योंकि अब हम Gaussian random process बोल रहे हैं, तो first we need to know what is a random process. And now, in order to study Gaussian random processes, we must know what is a Gaussian random variable. So this is the sequence of study. Okay. So I would be doing this revision in some sort, you can say, a faster manner because we have gone through it. So Gaussian random variable. So we will represent. This is a Gaussian random variable. So what we'll do is that if at all it is a random variable, then we'll use RV. And if I write here, if Gaussian random vector, suppose, which we will introduce, or I think we have gone through it, we will revise it because we need it for Gaussian random process. So if Gaussian random vector, it is denoted as RVec, okay? So that you nearly know what is a variable and what is a vector. This will be R capital. Okay, so there is a Gaussian random variable. We know that what is the density, because this has a density. This is a continuous random variable and it has a density which is called as Gaussian or normal, called as Gaussian or even most of the times normal. Okay, so if we represent this as random variable as x, then the PDF is P of x with a small x is equal to 1 upon root of 2 pi v square e raised to power minus of x minus m whole square divided by twice of v square. Okay, minus infinity into infinity. Okay, this will not have an equality. So this is the PDF, okay, where m is nothing but the ensemble average of x and v square is nothing but the variance of x. Okay, this is mean. So this we already know that this is the way we express the Gaussian density. This is 1 upon root 2 pi. V square is not inside. Okay, sorry, v square is inside. This is important. Otherwise, it has to be 1 upon v root 2 pi. So this is 1 upon root of 2 pi v square e raised to a minus of x minus m whole square divided by twice of v square. And this x takes values from minus infinity to plus infinity. Okay. Now, one important point. Okay, note. You can say that Gaussian. You can see that from this Gaussian density, what all you need to characterize it, you need only two numbers. That is m and v. So this is important. That Gaussian density. See, that's why there is, you can say, widespread popularity of this Gaussian random. One is that a lot of phenomena ultimately will have a Gaussian distribution because of central limit theorem. Another thing is that in order to study this random variable, or in order to, you can say, characterize its distribution, we only need two parameters. Otherwise, for other random variables, you may need more moments. It means this variance deals with up second moment, okay? Then you might need third moment, then you need fourth moment. So different moments also you may need to characterize the PDF of a particular random variable. But for the Gaussian case, you need only two moments. That is the first moment and the second moment, okay? So Gaussian density is completely so this is a fact which you must memorize, or we can just relate it to the PDF if you remember it. Completely characterized by its mean and variance. Okay. It is frequently, this is, you must know, this you remember, okay. It is frequently denoted, it is frequently denoted as, I think this you have seen, this is m comma v square. Okay, or you can say mu comma sigma square. I think this is just a change of notation. Otherwise, you know that the two parameters are mean and variance. That's why this is the way we don't write it down, because we only need these two moments, or you can say these two quantities, to express the full PDF of this random variable. Okay, that is the beauty. You only need two. So let us take an example. You already know this. Let me just write it down. This is suppose minus 5 comma 4. So I'm just drawing it. Okay, suppose this is minus 5. This is a small example, you say. For this is P of x, and this is your x. Just plotting the PDF. Okay, so this is an example. Minus 5 is the mean, so this bell-shaped curve would be centered around mean, that is minus 5, and this spread would be more or less governed by this variance, which is 4. So this graph is not to scale. I've just drawn it. If at all you need an exact, you can say graph, you can use MATLAB to plot this. Okay. So we use a shorthand. So in shorthand, this is why I'm writing it, so that you know that why we find these things in textbooks and other places. In shorthand, a Gaussian / normal. So I will write both, because RV with mean m and variance v square is denoted as, so that's why you will find this and with this operator. That is, this shows that this has a distribution which is, let us say, followed by this. Okay, that is the way we write things in shorthand. Okay. Then comes the concept of standard Gaussian random variable. Now the standard is simply the one which has a mean 0 and variance 1. Okay, so we will see how to do that. That is, x is 0, 1. Okay, this is called as the standard Gaussian random variable. Now one important point, let me do these important points with start. Yeah, important point is Gaussian random variables remain Gaussian. This is important. Remain Gaussian when we scale them. That's why what happens is we want to work with standard Gaussian random variables, because we can convert any Gaussian random variable with a particular mean m and variance v square into the standard one. Okay, with 0. Why? Because Gaussian random variables remain Gaussian when we scale them or add constants to them. Okay. In typical mathematical notation, this is called as, that is when we put them through an affine transformation. So this whatever I have written, that is scaling and adding, that is nothing but affine transformation. Okay. So in short, so whatever I am writing, I think these properties you will be using when you will be studying the receiver. Okay. फिर उस टाइम पे we won't be saying कि ऐसा कैसे हुआ, because हमने पहले ही देख लिया है कि ये properties हैं, कुछ को हम prove करेंगे, कुछ को prove के बिना हम लोग we will just simply accept them. Okay. So in short, if x is Gaussian, then ax plus b is also Gaussian. any constants. Okay. So this should be remembered. So we will do a small, you can say, exercise type of a thing, that how do you convert this. So if x is distributed like this, mean n minus p, then I think you must be knowing this, that this is distributed, right? So this becomes a standard Gaussian random variable. This is distributed noise 0. So what it is, that if you are given x, which has a mean m and mean is v square, you simply subtract the mean and divide it by the square root of variance, that is standard deviation, and then it becomes distributed like normal 0, 1. And this, I should draw it more properly in fast pace. This is the way generally it is. Okay. So now we will study things in the context of standard Gaussian random variables. Okay, because we know that any random variable Gaussian which has a mean m and variance v square can be converted to the standard format. So what is the CDF? So CDF of x is distributed as normal 0, 1, denoted as. So these are two popular integrals which x is. So these are two popular integrals which are very much used when you work with Gaussian random variables. That is probability that x is less than equal to small x, which is equal to nothing but minus infinity to x. You will find a lot of tables which will give this to you. Dt. Okay. And then comes the concept of CCDF. Okay. This is a complementary CDF. Okay. Let me write this is complementary. Now this complementary CDF is extremely popular in communication systems. CCDF of x, which is distributed as normal 0, 1, denoted as q of x, okay, is given as q of x. So this is very popular. You will find it at a lot of places. Once you will study this receiver design, you will find this there. So I am not defining how I am defining the integrals, because this you must be knowing. Okay, 1.2 pi. So you will find tables for qx as well as pi x. Okay, from the tables you can locate this value. Okay. Now a few properties. I think if at all you can see these two expressions. So first property is that q of x plus phi of x is 1. Okay. Then second property is q of minus x is equal to phi of x. And the third property is q of minus x is equal to 1 minus q of x. Okay. So these are three important properties which will help you see this q of x plus phi of x. You can easily see. If I am adding q of x to phi of x, it becomes an integral from minus infinity to infinity of the distribution. And we know that if at all this is a PDF, this must integrate out to 1. Okay, so this is 1. And the second follows from the symmetry of the Gaussian distribution. Let me tell you. So what is it? So if I am saying that this is 0, because this is the standard Gaussian random variable. So if at all this is the bell-shaped curve, and suppose I am saying this is x and this is minus x. So what is q of minus x? It simply says this, integrate this over this region, okay, towards the right. So this has this, integrate it like this. So you have to take the area of this region. And what is phi of x says? Phi of x says you just integrate from this, So this area from this to this has 0.5 value. Similarly, this to this has a 0.5 value. This goes, okay. So you can say that these two areas, that is A1 and A2, they are same because of this symmetric PDF. So you will find that this is equal. And this 3 follows from application of 1 and 2 together, okay. So this is important, this will help you. Let me just draw the graphs for, you can say these two Qx and phi of x. They are quite simple to see basically. Okay, if this is 0.5 and this is suppose 1, then you will find that this is like this. Basically, it's difficult to draw exactly what it is, but let me just try. Okay, this is what it is. This is Q of x, and this is phi of x. This is x, this is 0. So somewhat you can say they have a symmetric behavior because of the PDF itself being symmetric. Okay. One important thing that this fact 3, this implies that we need to consider guys, that we can consider only positive arguments for Q function while evaluating probabilities, okay, because they are directly related. Quite simple, because let us say if you have x as -3, then it's simply 1 minus q of 3. So you only need q of 3 to find it. This is just an observation, okay. So we'll do I think, I don't know if this example I should do or not. If you have sufficient background, I will do one example, one small example. So one small example is, if given that x is distributed as normal -3, 4, find probability that x is greater than 5 and so we have two. So let us solve the first problem. So probability that x is greater than 5. So we first normalize it. That is, if at all x is greater than 5, subtract the mean from both the sides and then divide by the variance. This should be greater than 5 plus 3 by 4. Okay. So this is same as saying that I am trying to find this probability. Okay. So this is same as saying this is Q of 4. This is equal to probability that greater than, this is what? This is 2. 5 plus 3 is, yeah, this is to be, sorry, this is 2 divided by 2 square root of this. This is nothing but Q of 4. this is equal to Q of 4. Okay. One more we can do is that, let me just do one more example. Probability that X is lying between 1 and 4. Okay, so that is to the second case. So doing similarly, you will observe that this is probability that this is 1 plus 3 by 2 less than x plus 3 by 2 and less than 4 plus 3 by 2, which is equal to Q of 2 minus Q of 3.5 or phi of 3.5 minus phi of 2. Okay. And then finally the third case. So what it is, that probability that x square plus x is greater than 2. This is same as saying if I now factor it out, that is x square plus x minus 2, which is greater than 0. That is what I need to find. So this is same as saying you just factor this. So this is x minus 1 into x plus 2 greater than 0. Okay, now this quantity, this product, because x takes positive and negative both values, so this product is positive if either both of them are positive or both of them are negative. Okay, so both positive needs x to be greater than 1. Okay, and both negative needs, what it means is x has to be less than minus 2, because if x is less than minus 2, this both will be negative. So union of these two will give me the answer. Union of these two should give me the answer. Now the issue is that while taking the union, if when I need to have one intersection, but these are two disjoint. If x is greater than 1, then x cannot be less than minus 2. And if similarly, if x is less than minus 2, it cannot be greater than 1. Okay, so it simply is addition. Intersection of both these events, is a null set. Okay, so simply add both the probabilities, that is probability x is greater than 1 plus probability that x is less than minus 2. So this should give you this probability that x square plus x is greater than 2. Okay, so this comes out to be Q of 1 plus 3 divided by 2 plus 5 minus 2 plus 3 divided by 2. Okay, so this is what a basic introduction to the Gaussian random variables and the standard Gaussian case. Okay, so before closing, I wanted to ask that because for the next 3 weeks I need one more lecture every week, because we are somewhat lagging behind as compared to section B, or we are lagging behind section B. So can we have a lecture tomorrow from 12 to 1:15? Means if anyone can respond to this. No, are you free if at all you are, or 2 to 3, whatever time suits all of you? So there is no reply. So basically we are done for today. Okay, so I will send an email